everybody. Today we're going to continue our discussion of rings by talking specifically about two special types of rings called integral domains and fields. You may remember that fields came up at the end of last video, and we'll reintroduce them here to remind you. Integral domains, on the other hand, are something new. So to tell you about what these are, I have to first tell you about two special types of elements inside of a ring. The first special type of element is what's called a zero divisor, which roughly speaking is an element in the ring that I could multiply by something non-zero to get zero. To put it more precisely, a zero divisor in a ring R is a non-zero element A in the ring R, such that there exists another non-zero element B in R, and when I multiply these two things together, A times B, I'll get zero. The other special type of element in a ring is what's called a unit. The definition is super analogous, except that when I multiply A and B, I'm looking to get not zero, but one. So more precisely, a unit in a ring R is an element A in R, such that there exists another element B, where when I multiply A times B, I get 1. Actually, because 1 is the identity element for multiplication, a more succinct way to say the definition of what a unit is that it's an element in the ring that has an inverse under times. I haven't phrased it that way in this definition because I wanted to really highlight the analogy between the definition of zero divisor and unit, but this is a great way to think about what a unit is. It's an element that has an inverse under multiplication. So let's look at some examples now. For instance, let's say we're in the ring Z6, where the operations are addition and multiplication modulo 6. Then 2, for instance, is a zero divisor. Why? Well, it's a non-zero element, and I can find something non-zero to multiply it by that will give me 0. Namely, in this case, 2 times 3 gives me 0. Notice that actually by the same token, 3 is also a zero divisor. On the other hand, the element 5, for instance, is a unit. Why is that? Because it's something that I can multiply by something else to get 1. In particular, in this case, actually 5 times 5 is equal to 1 modulo 6. Actually, in the example of Z6, almost every element in Z6 is either a zero divisor or it's a unit. But the one exception to that is the element 0. The element 0 is never going to be either a unit or a zero divisor. It's not a unit because there's nothing I could multiply it by to get 1. And it's also not a zero divisor because if you scroll back to the previous slide, you'll see that by definition, zero divisors are supposed to be non-zero elements that I could multiply by something to get 0. And so 0 by definition will never actually be a zero divisor. So I mentioned that in the ring Z6, almost every element is either a zero divisor or it's a unit. Something quite different happens in the ring Z of integers. In this ring, there are no zero divisors. Why? Because if I take a non-zero element of Z, there's never going to be anything I can multiply it by to give me 0. Right? If I take the number 2, for instance, there's nothing I can possibly multiply that by, nothing non-zero, that will give me 0. There are units in this ring. There's 2 of them. The units are 1 and -1. And why is that? Because those are the only 2 integers that have inverses under multiplication. Namely, 1 has an inverse which is itself. 1 times 1 is equal to 1. And -1 has an inverse which is also itself. -1 times -1 is equal to 1. But if I were to take any other integer, like again, let's say 2, it doesn't have an inverse under multiplication because 1/2 is not an integer. In particular then, most integers, like for example 2, are neither zero divisors nor are they units. So now, equipped with these two special types of elements of rings, I'm ready to define for you the two special types of rings that we'll be interested in. So here's the two special types of rings, and maybe just to kind of contextualize this, I'll tell you that the general philosophy here is that like zero divisors are weird and bad, and units are great. So I'm going to be looking for rings that either have very few zero divisors or a lot of units. So a ring with the fewest possible number of zero divisors is called an integral domain. Namely, an integral domain is defined as a commutative ring with unity such that there are no zero divisors. And then on the flip side, a ring with the largest possible number of units is what's called a field. We defined fields last video, but I'm going to phrase the definition a little bit differently now using our new terminology. Here I'll say a field is a commutative ring with unity such that every non-zero element is a unit. I'd love to tell you that every single element is a unit. That would really be as many units as possible. But as it turns out, it's just never going to be the case that 0 is a unit. So the best we can hope for is that every non-zero element in the ring will be a unit. So these are our two special types of rings. Let's look at some examples and non-examples of each. The prototypical example of an integral domain, and in fact I think this is probably the source of the name integral domain, is the integer z, right? Because we saw in the example a couple of slides ago that z doesn't have any zero divisors. That by definition is what makes it an integral domain. And by the same token, the real numbers, the rational numbers, the complex numbers, those are all integral domains as well. And why? Well, I want to make sure they don't have any zero divisors. In other words, I want to make sure that in any of these rings, if I take a non-zero element, there's never a way to multiply it by something non-zero and get 0. For instance, in the real numbers, I want to make sure, can I ever multiply two non-zero real numbers and get 0? And the answer is no. That's what makes R an integral domain. Similarly for Q and for C. We've already seen at least one non-example, on the other hand. Z6 is not an integral domain. Why is that? Because we found at least one zero divisor inside of Z6. Remember, we said that 2 was a zero divisor. And as soon as I've found a zero divisor, that tells me this must not be an integral domain. So that was some examples and non-examples of integral domains. How about fields? Well, for instance, the real numbers R form a field. And to know why that's the case, I have to convince myself that every non-zero element of the real numbers has an inverse under multiplication, right? That means any non-zero element is a unit. And that's true. If I take a non-zero real number a, then its inverse under multiplication is 1 over a, which is itself a real number. By the same token, the rationals q, or the complex numbers c, also form fields because I can take 1 over any non-zero rational number and get another rational number, or 1 over any non-zero complex number and get another complex number. But on the other hand, we've seen a non-example. The integers z do not form a field because not every non-zero element in the integers is a unit. For instance, 2 isn't a unit. 2 has no inverse in the integers under times. The thing that wants to be its inverse is 1/2, but 1/2 is not an integer. So that's the idea of integral domains and fields, which are my two favorite types of rings. We'll practice more with some examples of these in class. So I'll see you there.